it is not acceptable to run a bare grounding conductor inside rigid non-metallic conduit. National Electrical Code, Section 250.120c, states that insulated or bare equipment grounding conductors must be installed in a raceway or otherwise protected from physical damage. While this section doesn't explicitly prohibit a bare conductor in rigid non-metallic conduit, the requirement for protection is paramount. Rigid non-metallic conduit, as outlined in National Electrical Code Section 350.21a, shall not be used to support equipment. This implies that the conduit's primary function is to provide a protective pathway for conductors, not to serve as a structural support. National Electrical Code Section 300.3c further reinforces this concept, stating that conduits and raceways installed as electrical equipment grounding conductors shall not be used to support other equipment. This highlights the dedicated role of raceways in electrical systems. Moreover, National Electrical Code Section 300.3b mandates that conductors installed in raceways shall be protected against physical damage. The concern with a bare grounding conductor lies in its vulnerability. Without insulation, the bare conductor is susceptible to corrosion, abrasion, and accidental contact with other conductive surfaces within the conduit. Even within a non-metallic conduit, moisture can accumulate, leading to corrosion of the bare copper. Abrasion can occur during installation or due to movement within the conduit. An inadvertent contact can compromise the grounding path. The purpose of the grounding conductor is to provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. A compromised grounding conductor can impede this function, increasing the risk of electrical shock or fire. The code emphasizes protection against physical damage to ensure the integrity of the grounding system. While the conduit itself offers a degree of physical protection, it does not negate the inherent vulnerability of a bare conductor. Therefore, it is best practice and often interpreted as a code requirement to use an insulated grounding conductor within rigid non-metallic conduit. This provides an additional layer of protection against the aforementioned risks. In the specific scenario of a 100 amp Ethernet building using number 2 conductors with a bare number 6 ground in 2-inch polyvinyl chloride conduit, the installation is not compliant with best practices and could be considered a violation of the intent of National Electrical Code Section 250.120c. The bare number 6 grounding conductor should be replaced with an insulated conductor of the appropriate size. The size of the grounding conductor is determined by National Electrical Code Table 250.122 based on the size of the ungrounded conductors. For number 2 conductors, a number 8 copper grounding conductor is typically required. However, always consult the latest edition of the National Electrical Code and local amendments for specific requirements. The use of rigid non-metallic conduit, while providing physical protection, does not negate the need for an insulated grounding conductor to safeguard against corrosion, abrasion, and accidental contact. Always prioritize safety and compliance with electrical codes to ensure a reliable and safe electrical system. Furthermore, remember that electrical codes are minimum standards. Often, exceeding these standards with enhanced safety measures is a prudent approach. For example, using a larger grounding conductor than required or employing additional protective measures can improve the overall safety and reliability of the electrical installation. Grounding is a critical aspect of electrical safety, and any compromise can have serious consequences. Always exercise caution and adhere to established codes and best practices to protect people and property from electrical hazards. Also consider the environment in which the conduit is installed. If the conduit is exposed to direct sunlight, temperature extremes, or corrosive substances, the risk of damage to a bare grounding conductor is increased. In such cases, the use of an insulated conductor becomes even more crucial. Insulated conductors are available with various insulation types to suit different environmental conditions. Choose an insulation type that is appropriate for the specific application. For example, conductors with ultraviolet-resistant insulation should be used in areas exposed to direct sunlight. Conductors with moisture-resistant insulation should be used in damp or wet locations. and conductors with chemical-resistant insulation should be used in areas where exposure to corrosive substances is possible. The choice of conduit material is also important. While rigid non-metallic conduit is suitable for many applications, it may not be the best choice for all environments. In some cases, metallic conduit may provide better protection against physical damage and corrosion. When selecting conduit material, consider the environmental conditions, the type of conductors being installed, and the overall requirements of the electrical system. Proper installation techniques are also essential for ensuring the safety and reliability of the grounding system. All connections should be made using approved connectors and fittings. Connections should be tight and secured to prevent loosening or corrosion, and conductors should be properly supported to prevent strain on connections. Regular inspection and maintenance are also important for maintaining the integrity of the grounding system. Grounding conductors should be inspected periodically for signs of damage or corrosion. Connections should be checked for tightness and security, and any necessary repairs or replacements should be made promptly. A well-designed, properly installed, and regularly maintained grounding system is essential for electrical safety. By following established codes and best practices, you can protect people and property from the hazards of electricity. Finally, remember that electrical work should only be performed by qualified and licensed electricians. Electrical systems can be dangerous, and improper installation or maintenance can have serious consequences. If you are not qualified to perform electrical work, always hire a professional. They have the knowledge, skills, and experience to ensure that the work is done safely and correctly. They are also familiar with the latest electrical codes and regulations. Hiring a qualified electrician is an investment in safety and peace of mind. Before hiring an electrician, check their credentials and references. Make sure they are licensed and insured. Ask about their experience with similar projects, and get a written estimate before work begins. A reputable electrician will be happy to answer your questions and provide you with the information you need to make an informed decision. In summary, the use of a bare grounding conductor and rigid non-metallic conduit is generally not recommended due to the potential for physical damage and corrosion. The National Electrical Code requires that grounding conductors be protected, and while the conduit provides some protection, it is not sufficient to negate the inherent vulnerability of a bare conductor. Insulated grounding conductors should be used in all conduit systems to ensure the safety and reliability of the electrical system. Always consult the latest edition of the National Electrical Code and local amendments for specific requirements. And always hire a qualified and licensed electrician to perform electrical work. The code also addresses the ampacity of conductors. Ampacity refers to the current carrying capacity of a conductor in amps. The ampacity of a conductor is determined by several factors, including the size of the conductor, the insulation type, and the ambient temperature. National Electrical Code Table 310.16 provides ampacity ratings for various types of conductors. It is important to select conductors with an ampacity rating that is sufficient for the load they will be carrying. Overloading conductors can cause them to overheat, which can lead to insulation damage, fire, and other hazards. The National Electrical Code also addresses voltage drop. Voltage drop refers to the reduction in voltage that occurs along the length of a conductor. Voltage drop can be caused by the resistance of the conductor and the current flowing through it. Excessive voltage drop can cause equipment to malfunction or fail to operate properly. The National Electrical Code recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, use larger conductors or shorten the length of the circuit. The National Electrical Code also addresses overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Overloads occur when the current flowing through a circuit exceeds its ampacity rating. Short circuits occur when there is a direct connection between two conductors of opposite polarity. Overcurrent protection devices will trip or blow when an overload or short circuit occurs, interrupting the flow of current and preventing damage to the electrical system. It is important to select overcurrent protection devices with the appropriate ampacity rating for the circuit they are protecting. The National Electrical Code also addresses grounding and bonding. Grounding is the process of connecting electrical equipment to the earth. Bonding is the process of connecting different metal parts of an electrical system together. Grounding and bonding are essential for electrical safety. They provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. They also help to reduce the risk of electrical shock. The National Electrical Code also addresses wiring methods. Wiring methods refer to the way in which conductors are installed in an electrical system. There are many different wiring methods available, including conduit, cable, and raceway. The choice of wiring method depends on the application and the environmental conditions. The National Electrical Code specifies the requirements for each wiring method. The National Electrical Code also addresses equipment installation. Equipment installation refers to the way in which electrical equipment is installed in an electrical system. The National Electrical Code specifies the requirements for the installation of various types of equipment, including panel boards, transformers, and motors. Proper equipment installation is essential for ensuring the safety and reliability of the electrical system. The National Electrical Code is a comprehensive set of standards for the safe installation of electrical systems. It is important to consult the National Electrical Code and local amendments before performing any electrical work. Always hire a qualified and licensed electrician to perform electrical work. Remember that the information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician for specific recommendations and to ensure compliance with all applicable codes and regulations. Ignoring electrical codes can lead to serious safety hazards, including electrical shock, fire, and equipment damage. It is essential to prioritize safety and follow established codes and best practices to protect people and property from the dangers of electricity. This may also lead to failure of the electrical system, including but not limited to short circuit, fire, damaged equipment, or electrical shock. Ensure all electrical work is done professionally and inspected to ensure compliance with all applicable codes and regulations. Regular maintenance and inspection of electrical systems are also crucial for preventing potential hazards. Damaged or worn-out components should be replaced promptly, and any signs of electrical problems should be investigated and addressed immediately. Electrical safety is a shared responsibility, and everyone should be aware of the potential hazards and take precautions to prevent accidents. If you are unsure about any aspect of electrical safety, consult with a qualified electrician. The cost of electrical safety is minimal compared to the potential consequences of neglecting it. Prioritize safety and make sure that your electrical system is safe and reliable. Remember that electricity is a powerful force and should be treated with respect. By following established codes and best practices, you can ensure that your electrical system is safe and reliable for years to come. Consider the impact of environmental factors on the grounding system. Soil conditions, moisture levels, and the presence of corrosive substances can all affect the performance of the grounding electrode. In areas with poor soil conductivity, it may be necessary to install additional grounding electrodes to achieve the required grounding resistance. Regular testing of the grounding system is also recommended to ensure that it is functioning properly. The grounding resistance should be measured periodically and compared to the recommended values. If the grounding resistance is too high, corrective action should be taken to improve the grounding system. This may involve adding additional grounding electrodes, improving the soil conductivity, or replacing corroded components. Furthermore, be aware of the specific requirements for grounding different types of equipment. Some equipment, such as sensitive electronic devices, may require special grounding techniques to prevent noise and interference. The National Electrical Code provides guidance on grounding requirements for various types of equipment. Follow these guidelines carefully to ensure that the equipment is properly grounded and protected. Never attempt to modify or alter the grounding system without consulting with a qualified electrician. Improper modifications can compromise the safety of the system and create potential hazards. The grounding system is a critical component of the electrical system, and it should be maintained in good working order at all times. Regular inspection, testing, and maintenance are essential for ensuring its safety and reliability. Remember, electrical safety is a continuous process, and it requires ongoing attention and effort. By staying informed, following established codes and best practices, and consulting with qualified professionals, you can create a safe and reliable electrical environment for yourself and others. Grounding systems have several important functions. Firstly, protecting people from electric shock by providing a low impedance path for fault current to flow back to the source, causing the overcurrent protective device to trip and de-energize the circuit. Secondly, preventing the buildup of static electricity, which can damage sensitive electronic equipment or ignite flammable materials. And thirdly, providing a stable reference point for electrical circuits, ensuring proper operation of electrical equipment. A properly designed and installed grounding system is essential for achieving these functions. The grounding electrode is the most important component of the grounding system. It is a conductor that is buried in the earth and connected to the grounding system. The grounding electrode provides a direct connection to the earth, allowing fault current to flow back to the source. There are several types of grounding electrodes available, including ground rods, ground plates, and underground metallic water pipes. The type of grounding electrode used will depend on the soil conditions and the requirements of the electrical system. The grounding conductor is another important component of the grounding system. It is a conductor that connects the grounding electrode to the electrical equipment. The grounding conductor provides a low impedance path for fault current to flow back to the source. The size of the grounding conductor must be sufficient to carry the maximum fault current that could occur. The bonding conductor is a conductor that connects different metal parts of the electrical system together. Bonding helps to equalize the potential between different metal parts, reducing the risk of electric shock. All metal parts of the electrical system should be bonded together, including conduit, enclosures, and equipment housings. Surge protection devices are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power line switching, or other electrical disturbances. Surge protection devices divert the surge current to ground, preventing it from damaging electrical equipment. Surge protection devices should be installed at the service entrance and at sensitive electronic equipment. Ground fault circuit interrupters are used to protect people from electric shock. Ground fault circuit interrupters detect small imbalances in the current flowing through a circuit. If an imbalance is detected, the ground fault circuit interrupter will trip and de-energize the circuit, preventing electric shock. Ground fault circuit interrupters are required in all wet locations, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters are used to protect against fires caused by arc faults. Arc faults are caused by damaged or deteriorated wiring. Arc fault circuit interrupters detect the characteristics of arc faults and trip the circuit, preventing fires. Arc fault circuit interrupters are required in all branch circuits that supply bedrooms. Electrical safety is a serious matter, and it is important to take all necessary precautions to prevent accidents. By following the National Electrical Code and best practices, you can create a safe and reliable electrical environment for yourself and others. Grounding and bonding are critical for electrical safety and performance.